Alright, let's talk about transformers. And when I say transformers, I'm not talking about these guys. I'm talking about these types of things right here. So, what voltage comes out of a wall socket here in North America? It's about 120 volts. Yes, maybe it's 110 volts, depending on where you are and where it's being distributed from. Um, so what are the odds that your dishwasher, for example, and your clock radio both need the exact same voltage, 120 volts? Like, when you look at your clock on your nightstand, do you think it needs the same amount of energy as a dishwasher, or as your washing machine, or as your refrigerator? That seems crazy that they both would need the same amount of voltage. So the answer is small. Yes. So what some products need are a transformer. Many products use a transformer to convert electricity to another voltage. Yes. It's sometimes like this picture right here. This is a little tiny transformer. We'll often call them adapters. Yes. Sometimes it'll be plug thing in the thing before I get to my, let's say, laptop. Yes, it's my laptop right here. Sometimes it's in the cord. Sometimes it's here where we plug in. Sometimes it's inside the device. But many things have them. Okay? Transformers are used to change the size of AC voltage. Usually I'm taking it from 120 to some other amount that device needs. And all devices are made differently and would have a different little type of transformer inside them. Transformer, we looked at this type of setup before. It's a transformer is a metal core, a primary circuit, and a secondary circuit. So if I have AC current here, the current is always changing. It's always making a magnetic field in this piece of iron, and then that always changing magnetic field will be making an always changing current here. So magically current comes here, and without touching anything, none of these things are actually touching each other, I'm getting current flowing over here. Just a reminder, if you use a DC current, the magnetic fields would not always be changing, and so a current would not be induced in the second coil, a constant one. It would be just for an instant and then it would stop. So the size of the secondary voltage, the voltage over here, depends on the turns. So scientists figured out the number of turns over here, or coils or loops over here and here. If we vary them, I can get the voltage here to either be higher or lower than it is on this side, which is the whole basis of a transformer. There's a formula, of course. In physics, we ruin everything with a formula. The voltage in the secondary, voltage in the perpendicular, and the n is the number of turns, which is really fantastic idea. So using this idea, so if I have here and I have that many turns over on the other side, I don't know, if I count here, maybe the ratio is 2 to 1. So I would get the voltage, if it comes in at 120, it would only be 60 over here by varying the number of turns, and then I can get my device to have the proper amount of voltage to make it run. Now I guess the other way, if 120 volts goes in to a device, I either use a transformer or I could put in some resistors. Yes? That would use up some of that voltage if I think about the shopping rule. But the problem with this is that resistors use up energy all right, but they use it up and release it as heat. And it would suck if my clock radio, for example, instead of having a transformer in it, had resistors in it, and it got really warm all the time and it was constantly kicking off heat. That would be not very practical, not very useful. So instead of using a resistor, which would be it's a solution to the problem, it's just not a good solution. That's why we go with these transformers or adapters. Transformer is not 100% efficient. Not all the input electrical energy is transferred to electrical energy at the output. Some heat is always generated. You'll also they hum, so it's not 100% efficient. The relationship between the voltages and the currents between the two coils. Here's our formula: S's and P's again. You'll notice that the VS is on the top over here and IS is on the bottom. So as V goes up, I is going to go down. We have an inverse relationship here. Where do I use transformers? They waste energy that goes through them. They generate huge voltages, and then you have to make the voltage saving. So they're very important for transmitting electricity. Power stations make electricity at 25,000 volts. And then the first thing they do before it leaves the factory, the production facility, is that they put it in a transformer, and they ramp it up to huge voltages. Why do we use these huge voltages? Well, like I just said here, as V goes up, I goes down. And when I look at power loss, low current is important. If I look at power, and there's a bunch of formulas for power, power gets bigger if power goes up. Well, let me rewrite this. If I goes up, power goes up, and I think it's a squared relationship. So we really don't want I to be big. We want I to be as small as possible because of this squared relationship. So we want the current to be really small. And now you might think that there's not going to be a lot of resistance in wires, but electricity has to be distributed down kilometers and kilometers of cables. The cables are made to have very low resistance. But because they're so long, the network is so huge, you're still going to be losing so much. I've heard estimates, and I believe it, that we lose way more energy getting electricity to your houses than is actually used in homes. That's how much electricity we're losing here. So we need to try to minimize that, and we would minimize it when we'd minimize it when the voltages are high and the current is low. Right? We resistance gets smaller, or because of resistance, the power loss gets smaller. So we want high V's, low I's when we're transporting it. So what happens is we have our power plant. The V goes up. We make the I go up. We send it down the power lines to a little transformer. It takes V, it drops the V down, yes, and I up. That's I is down. Sorry, people. Just before it goes into your house, yes. This means more useful electricity for you and me to run our computers, yes. And only, like I just said, only when electricity reaches your neighborhood is it transformed back into the 120 volts. Yes, we see them, you might have seen them look like this, or these. These are all different transformers. Each one would be different. Transformers, if let's say the electricity is coming from Niagara Falls, we are further away from Niagara Falls than Toronto, so transformers in Toronto would be different than the transformers in Belleville, which would be different than the transformers in Kingston, because the voltage or the amount of power that gets to our homes in these places would be different. The amount of that's lost on the journey is different. So all these transformers that you see are custom built to change the electricity that's arriving to them to the perfect amount just before it goes into your home. So that's our little look on transformers.